So what is the Voronoi diagram? Well, suppose you have, so let's just focus on a single point. So imagine this is one of the documents in your uh, overall vector space, and let's say there are some other documents around it. Now let's identify, so let's start from here and let's visit each of its neighbors in the clockwise direction. What would be the region that, so let's focus on these 2 points. If we were to divide this entire vector space into 2 regions, one of the regions consisting of points closer to this and the other region consisting of points closer to this, how would we create that region? Well, we would join these 2 points by this line segment and then draw a perpendicular bisector to it, kind of like this. So everything to the left of this line would be closer to this point than to this point. Now let's focus on these 2. Again, we can draw a line segment and then divide the entire vector space into 2 regions, one closer to this circle and the other closer to that circle. Then when we look at this particular neighbor, we'll again draw a line segment, divide it into 2 regions. Then when we look at this particular neighbor, we'll have a line segment over here, and then we'll divide it into 2 regions. Likewise for this particular neighbor, we'll have a similar, we'll have a line segment here. When we perpendicularly bisect it, we may get something like this. And then when we look at this final neighbor, we'll get another line. So if you look at all the regions put together, then this particular shaded region consists of points that are closer to this central, it's not necessarily central, but closer to this circle than to any other point in your vector space. Okay. Notice that the shape of this region is a convex polygon, and as you can imagine, you can repeat this exercise for all of the points and you will get similar convex. Well, this is a closed polygon. For some of the points, the region may extend indefinitely into into the space. For example, if you have a boundary point, then you can imagine that everything on the other side of that point, so there are no other points on that side, so that region will continue indefinitely up to all along the infinite space in that direction. So this Voronoi diagram is a diagram that's generated as a result. There are many analogies you can give to this. For example, if you think of each of these points as a cell phone tower, and then the Voronoi region for every point is the region that the tower serves. Or if you think of each of these points as different stores of a supermarket chain, then the different regions correspond to residential areas which are served by that particular store. Okay, so if I am in this particular region and if I had to go to the nearest store, then I would go to this particular store, assuming that the distance to this store is just given by the straight line distance from wherever I am. So that's the Voronoi diagram that you can see over here. So if you draw this Voronoi diagram for all the documents in your vector space, and let's say you have 2 classes of documents, a circular class and a non-circular class, where each document is represented by a cross. then you can come up with a decision boundary which will separate a document from the circular class from a document in the non-circular class. And that would be this particular region. You can see that it's consisting of a number of broken line segments which separate the circular class from the cross class. And any point corresponding to a test document will be classified by looking at the nearest neighbor. So remember that we are looking at 1 and n. We are looking at k equal to 1. So since this point falls into the cell of this circular document, it clearly belongs to the circular class. So contrast this. So this is called a nonlinear classifier. So imagine a classification problem where there are only two classes, like in this example. The decision boundary between the two classes is not a straight line, or in v-dimensional space, if you extend the straight line, it will become a hyperplane. So this is not a hyperplane. This is a series of broken hyperplane segments. So the k nearest neighbor algorithm is an example of a nonlinear classifier, because for a nonlinear classifier, the decision boundary between two classes is not a straight line, or in higher dimensions, it's not a hyperplane. It's a more complicated surface. Whereas if you had the Rokio algorithm, right, imagine these same points, these circular points and these crosses existing in v-dimensional space, and you had to come up with a decision boundary for based on the Rokio algorithm, then that would be much easier, because if I have a bunch of crosses and if I have some circles, I just have to compute the centroid of this particular region of this particular class and the centroid of this particular class. And my decision boundary is going to be the perpendicular bisector of this line segment between joining the two centroids. So it's going to be something like this. It's going to be a straight line or a hyperplane in higher dimensions. So everything to the left of this line is closer to this centroid than to this centroid. Everything to the right of this line is closer to this centroid than to the other centroid. So this is the Rokio algorithm is an example of a linear classifier, because when you have two classes, the decision boundary between them is given by a hyperplane. Any questions about what a decision boundary means, and how it could be linear and how it may not be linear? So it will not be linear. Yeah.
So why would it not be linear in some cases? Because like in all the cases we are drawing the perpendicular bisector, right? So why would it not be linear?
Well, you can see here, right? If you look at if you look at the cells over here, so this is the Voronoi diagram that's resulted from the one nearest neighbor algorithm. See how you separate documents in this circular class. Actually, there are three classes over here. You may not be able to distinguish that these are diamonds, not circles, whereas these are circles. So you have this series of broken line segments going like this, and then you have another series of broken line segments like this, separating the circular class from the diamond class. So just look at this diagram and see why would you get a linear, why would you get a straight line over here if you use the k nearest neighbor? You will get a straight line if you use the Rokio algorithm on this particular, on the same set of points. Okay, you'll get three different. I mean, between any two classes, you will get a hyperplane. For now, just imagine that there are two classes. So you can ignore this particular part because let's say we merge together all these documents and say they're all circular. Then your boundary will be this series of broken line segments. So what's your question? Are you asking why will this not be a hyperplane?
Why not a straight line actually? I mean that's what I.
That's
Okay, sir. You should.
so
So is it like
yeah.
is the k nearest? Is it because it's the k nearest neighbors? Like we do, the neighbors are differently distributed. Is it because of that that it's like this, the
Yeah.
shape?
Yeah, so this is an artifact of the algorithm. If that's what I said. If you use the Rokio algorithm, you will get a straight line because then you will have two centroids and the algorithm, as I will just show in a few minutes, will generate a hyperplane as the decision boundary, which is going to separate the two sets of points via that particular boundary, which will be a hyperplane. Whereas this is an artifact of the k nearest neighbor algorithm that you don't get a single hyperplane, you get this series of broken surfaces. It's a more complex surface. So it's not a linear
So,
classifier. Yeah.
so, sir, I wanted to ask, what is a hyperplane, sir?
Okay, let's look at that. So let me try to explain to you why the Rokio algorithm is a linear classifier, and we'll see what a hyperplane is in that context. Um, Actually, um, let me first do this example with you before I go there, because recall that this was an example where so we are going to look at the same examples that we ran on the Rokio algorithm and see how the classification could be slightly different, or how the classification works in general. So let's take k equal to 3. Okay, so we are going to look at the three nearest neighbors to our test document. So there are two classes here, three documents in one class, two documents in the blue class. So now we get a test document. What do? We will look at the three nearest neighbors, which are going to be these three vectors. Two of them are blue, one of them is red. So 2 is the majority vector, right? 2 is the majority vector, and so this test document, will be colored blue. Let's look at the other example we did. Okay, recall that this was an example where the Rokio algorithm does not do very well because you don't have a contiguous region of space representing the red class. The red class is split across two clusters or two regions. One region over here, the other region over here, and then you have this middle region corresponding to the blue class. So let's say your test document is given by this black vector. Now you will again use the three nearest neighbor algorithm, and you can see that two of the nearest neighbors are going to be blue, okay, and the third one will be red. Now because you're looking at the neighborhood of this particular vector, the immediate neighborhood is mainly blue, and so this document will be classified as a blue document. Whereas in the Rokio algorithm, what were we doing? We are computing the centroid of the blue documents, which would fall plumb in the middle of this blue region, okay, leading to a potential misclassification. So you see why the three nearest neighbor does better for such examples where your classes are not contiguous regions, but they are sort of split into more than one cluster, like this red class. In that case, it's better to look at the local neighborhood that you are in to decide where you go.
Okay, sir. Sir, but would it depend upon the problem to decide which one to use? Like,
Yeah, yeah. So uh, if your if your application looks like the looks like one where your classes are going to be contiguous in space, then it may make sense to use a linear classifier. But if your classes are not going to be in, clusters, if they're going to be broken apart, right? Another example, let me give you another example, which is, look at this example. So this is an example. Here you have many more points, but you can see that there are two classes over here. There is one class consisting of these uh, black circles, and this particular class is represented not only by this approximately triangular region, but also by this circular region over here. Okay, and the other class is represented by documents that are denoted by these little squares. Now, there is no way to draw a straight line in this diagram that will cleanly separate the darkened circles from the squares, right? Imagine, can you think about this question? Can you draw a any straight line either like this or like this or like that, which can separate the documents in one class from the documents in the other class? No, you can't. So we say that these documents, these set of points are not linearly separable. Okay, what do we mean by they are not linearly separable? You cannot draw any straight line which will cleanly separate the two classes. So linear classifiers won't work well on such data. But if you use the k nearest neighbor algorithm, it'll do very well, because if you're looking at points in this particular region, and let's say your test document falls in this region, then you will classify it into the circular class. Whereas if it falls into this particular region, then you'll classify it into the other class. So you're looking at your local neighborhood and then making that decision. So that's the thing. If your application is such that you expect classes to be of this particular form, where your data will form independent clusters, then it's better to use the k nearest neighbor algorithm. Whereas if your classes are such that they will fall into contiguous regions of space, then you can probably linearly separate them, and then you can use linear classifiers for that. Any other questions? One thing I want to mention about the k nearest neighbor algorithm is that even though in the test phase you don't need to do any work, if you think about even though in the training phase you don't need to do any work, because in the training phase you're not building any model, in the test phase you will need to do a lot of work, because you have to compute which document is closest to your test document among all the documents in the vector space. So how do you compute your nearest neighbor? Well, you will have to compute the distance between the test document and every document in the vector space, and then choose the nearest neighbor or nearest neighbors depending on what the value of k is. So finding the nearest neighbors is going to require computing distances to all the D documents in your collection. Now note that this is not what you did in naive Bayes or Rokio. In Rokio, all you did was you computed your distances to every centroid. So the number of distances that you had to compute was the number of classes that you had. Whereas in k nearest neighbors, the number of distances you have to compute in the test phase is the number of documents you have in your collection, which is huge. So how do you optimize it? How do you speed this up? Well, one way you can speed it up is to exploit the ideas that we have discussed in the first half of the course. How do you build an inverted index and speed up, chapters 1 to 7 basically. How do you build an inverted index from a collection of documents so that given a query, you can quickly find out which documents are close to the query. So you can build an inverted index on these D documents and think of your test document as a query. Okay, so think of your test document as a long query. So you build this inverted index, and determining the k nearest neighbors is the same as determining the k documents that have the best rank, the ranking score, with respect to your query. Right, so that won't require you to examine every single document in the collection, because you will just look at the relevant postings lists in your inverted index corresponding to terms in your test document. And then you can use the optimization techniques that we discussed in your chapter 7, which can speed up your even this kind of retrieval. Okay, so using standard vector space inverted index methods can speed up finding the k nearest neighbors. Is that clear? Forget about this. Basically, you won't have to look at all D of the documents. You will only have to look at um, a smaller number of documents. Okay, based on depending on how many documents there are in the postings list for the relevant terms. Okay, that's all that this is saying. So some of the advantages and downsides of k nearest neighbor. Firstly, forget about this point, no feature selection. I don't think I discussed feature selection with you in detail when we talked about naive Bayes, but feature selection just refers to narrowing down the set of terms in your documents so that your document representation is more meaningful. Okay, for example, you could remove stop words. You could remove words with very low IDF score. So focusing only on the important words in your documents will reduce the size of your document vector. It will reduce the number of dimensions you have in your vocabulary, because you're throwing out of your vocabulary all terms which are stop words or which don't really help you to differentiate one class from another class. So that's what is called feature selection. Term that you're each term that forms the axis in your vector space is a feature, basically, because each dimension in your vector space is a feature. So reducing the number of dimensions you have is what feature selection is. Picking out those dimensions or those terms which are more important. K nearest neighbors also scales well with the large as the number of classes grows, because all you have to do is look at the local neighborhood. In fact, you're not even looking at any model for any class. You're not building any model for any of the classes. You don't even care what classes there are. All you do is you find out which are the closest documents to me, and then look at their class labels and see which is the majority class. Contrast that with the other algorithms where you have to build some kind of a model for every class. Now classes can also influence one another, because if you add, say, more number of documents to a training class, it's possible that your local neighborhood may change. So classes can influence one another. And in general, your scores can be very hard to convert to probabilities. So in your naive Bayes algorithm, there was a clear probabilistic interpretation of that algorithm. This algorithm is very hard to interpret in terms of probabilities. It requires no training phase. And I mean, in some ways it does. I mean, when we talked about feature selection, I said that you may want to pre-process your documents to reduce the number of terms in it. So that can be some pre-processing that will be required in the training phase. But conceptually, there's no training. But the test time is very expensive. Okay, even though it can be optimized in the way that I just described by using an inverted index. And in most cases, it's more accurate than naive Bayes or the ROQ algorithm.